So my name is Jim. I'm going to talk about how we can access data in the Lakehouse from Python and using two technologies, one called ArrowFlight and the other called DuckDB. And if you don't know anything about lakehouses are a new type of data warehouse where the data is stored in a data lake. So they're low cost and they give you much of the functionality you'll find in a data warehouse. So you get asset updates, time travel, and great stuff at low cost. So it's a very interesting place to store a lot of data. There are some competing table formats out there. There's been talk today about Apache Iceberg, but you also have Apache Hudi and Delta Lake. Ultimately, they all store their data in either Parquet files or ORC files. It's tabular data, but what they've done is they've been designed really for the big data world. So you'll see that there's clients for writing the data in Spark or clients for writing the data in Flink. And then there's query engines for reading the data. So you can have Trino or Dremio and Snowflake and others in BigQuery can read the data in Iceberg, for example. But what happens to Python? We have a lot of Python developers out there. A lot of them like to use Pandas, more using polars. Some could even use DuckDB. How can we get at the data, the increasing volumes of data that's being stored in the Lakehouse table formats from Python? So that's what I'm going to talk about today. I'm going to talk specifically about Hudi, where we've been doing work, but I think a lot of it applies also to Iceberg and Delta Lake. And I'm going to start by talking about why we did this. Well, the reason we do it is because we're interested in building machine learning systems, and particularly with a feature store, which I'll get into in a second. But machine learning systems you can see as being effectively machine learning pipelines that are chained together. And I don't tend to use the word machine learning pipeline because it's not well defined what the input and output is. So we normally talk about a feature pipeline that takes raw data, outputs features and labels. Training pipelines take features and labels and output a model. And inference pipelines take a model and new features and they'll output predictions, whether it's online or batch inference. So given that this is a kind of typical machine learning system, the challenge we had was that in our feature store, HopsWorks, we store the offline data, the historical feature data in Apache Hudi. We're also looking at Iceberg, but at the moment we support Apache Hudi. And we can write the data in the feature pipeline. And you can write it in Python, you can write it in Spark, you can write it in Flink. But when you write it in Python, currently what we do is we write it to an intermediate layer, to Kafka in fact, and then we run a Spark job to write to the Hudi tables. So we're using something called Delta Stream for that. And that's not exactly ideal. And then when you're reading data into Python, your training pipeline's nearly always written in Python. And if the data you're going to train your model on is in a table format like Hudi or Iceberg, how do you get the data out with high performance? And the same is true for inference pipelines. So online inference is nearly always in Python. How do we get the data out efficiently? So under the hood, the feature store is actually a dual database system. You have this offline store that I'm going to talk more about, where we store all of the historical data, typically in these table formats. And then there's also a low latency store, a row-oriented store for getting really low latency access to the latest feature data. And the feature store is used to basically manage your data for machine learning. You have the pipelines that feed it in, and then we have training API for getting training data back, batch API for getting batches of data frames back for batch inference, and then also row-oriented API for getting feature vectors for online models. So we've been working with this for a few years. Our feature store was the first open source feature store, and we've provided Python access via JDBC. Right? So this kind of works. Like, we have a serverless version of HopsWorks. It's got over 4,000 users on it. And they're using JDBC to download. They have been using JDBC to download the feature data stored in this table format into a Python client. And it kind of works okay for small amounts of data, but it's really slow. So we really needed to fix it. And what we've done, and what I'll talk about today, is how we changed using JDBC to using Apache Arrow, and we also changed the internal. So we changed from using Spark and Hive as our query engine to using DuckDB. So this is DuckDB, as many may know, it's an embedded columnar store. This is an architecture, I would say, that's suitable for what we call reasonable scale data. So if you're going to ingest data on the order of 100 gigabytes, or if you're going to read data 100 gigabytes or less, that's reasonable scale. You can do it with these technologies. Okay, so let's get going on it. Before we do, the short note is we got a huge speed up. So effectively, what's happened is using a feature store, which all of the existing feature stores have this JDBC API, they're very slow. And it's not funny that feature stores don't have a great reputation amongst Python developers, because when you want to just get a gigabyte of data, it's taking 20 minutes, right? And that's not reasonable. Not for anybody who can get a gigabyte of data from their laptop, their Mac Pro in a few seconds. So what we see with using Arrow and DuckDB is we're now getting network line speed, which is pretty incredible. So let's get into it. I'm going to start, if you don't know what Apache Arrow is, it's an open source columnar in-memory format. It's an in-memory data format, I should say, to be explicit. So if you look in the chart here, you can see that there's, at the top of it, we have rows, row 1 to 4. And you can see you've got these different columns that are colored blue, green, and red. So that data is stored at the top in what we call row-oriented format. We have each row is stored contiguously in memory, and it's efficient when you want to retrieve a row of data. So a key value store can do this efficiently, or even a database, a relational database that allows you to do projections. You can say, just give me row 1 in the first column. And if you want to store that efficiently for analytics, columnar formats are more efficient. So if we pivot that data, and you can see we have the Arrow memory buffer at the bottom corner of the screen, you can see that we're now storing the data contiguously in memory by column value. So we store all of the timestamp values contiguously one after another in memory. And this means it's much more efficient when you do analytics or query processing on the data in memory, when you're doing typical analytical operations. So if you're computing aggregations or doing complex joins and those type of operations. So apart from the memory layout, the columnar memory layout, we also have zero copy reads, which is very useful, and we'll exploit that today in our architecture. What that basically means is that if we're transferring Arrow data from one process to another, we may not need to deserialize and serialize the data. So those of you who are familiar with Apache Spark will know that there's been something called Pandas UDFs there for quite a while. And Pandas UDFs are a very efficient way of implementing functions that take Pandas data frames as a parameter, and then they return a Pandas data frame or a series. And what they do is they transfer data from core Spark data frame to these workers that execute Pandas code, so vectorized Pandas operation on the Arrow data, and there's no copy involved. So typically in Spark world, if you're running PySpark, there would be a copy of data that would be deserialized from the JVM into the Python code. If you run a Python UDF, it'll deserialize it and send it back, and it's all very slow. So Arrow's had been there for a few years and been very successful, but we'll see today that we use it also to transfer data from the Lakehouse all the way to Pandas clients. And if you're familiar with Pandas, you may know that last year, or earlier this year, Pandas 2.0 changed its internal memory format to Arrow. So previously it was NumPy, and now it's Arrow as its internal native format. So there is another technology that we're interested here, which is called ArrowFlight. So ArrowFlight is it's an RPC protocol. It's a way of transferring data from a client to a server, from a server to a client. So the client would say, hey, I want some Arrow data, and it returns the data in Arrow format. So Arrow is in fact also an over-the-network transport protocol format. So you can send the data in Arrow, it's checksummed, and the client will validate the checksums. And you can send the data straight over. And if you compare that with, let's say, a table you have and you want to send over JDBC, in JDBC it's going to serialize the data and then deserialize it on the other side. So what we can do when we have a Pandas client, because if we go back and say, well, we want to build machine learning systems, we're going to have these training pipelines implemented in Python. They're going to receive the data in Pandas. They're going to train their models, and same with our inference pipelines. They're going to be in Python. Don't want the data in Pandas. And what we wanted to do, and we saw that, well, hang on, ArrowFlight looks really, really promising compared to JDBC, because we can send Arrow data in an Arrow table to a client without needing to deserialize or serialize the data. And we also don't need to, compared to JDBC, do what we call a column to row pivot. So if our data is in JDBC, it's in row-oriented format. And when we want to use the data in Pandas, we want it in column-oriented format in Pandas. So that means you might have to pivot the data from JDBC to Pandas. So if we can avoid all that, it's great. And we looked at some of the literature that's out there. Dremio have done quite a good bit of work in the space on ArrowFlight. You can see some numbers here comparing JDBC and ArrowFlight. The blue lower is better. In this case, it's the amount of time taken to transfer data, columnar data, from a client to a server. And these were done by Dremio, these experiments. But you can see it looks very promising compared to JDBC. So even ODBC is not great here. There's not much difference because ODBC is also a row-oriented network protocol. So if you have columnar data and you want to transfer it from a client to a server, ArrowFlight is very interesting. There is a new protocol called ADBC, so Arrow Database Connectivity, which is a layer on top of ArrowFlight. So it's basically like a JDBC driver that you would install, and you could read from then a server that's returning Arrow data to the client. But we looked at ArrowFlight as a kind of a more narrow option because we want to just get back feature data for machine learning. It's not a general purpose SQL API yet. So ArrowFlight really promising. We had another issue that we saw internally with our feature store, which was we were using Spark as the query engine. And a feature store has data spread over many tables. We call them feature groups. And we have to join features together with our label in order to create training data sets. This join is quite complex. It's called a point-in-time join. It's actually kind of a complex left as of, a left outer as of join, or as of left outer join, outer left join. And Spark's very slow at it. You have to implement it yourself. We looked at different techniques. We made some optimizations compared to the Spark query engine. It's still not great. But DuckDB has a native implementation of that join, which is very highly performant. So DuckDB is an analytical database management system. It's a columnar store, kind of like Databricks or Snowflake, but with no dependencies, and you can install it inside your application as an embedded library. You can install it in a Jupyter notebook. You can pip install DuckDB, and then you can send string. You can read up data into it. You can, execute SQL queries on it, and it's really fast. It's competitive with even Polars, which is a very high-performance data frame processing engine in Python. You can put it inside ETL pipelines. You can do what we did. So what we did was we put it inside our server. So we have an ArrowFlight server. We have DuckDB inside of it. And DuckDB is now going to do these point-in-time joins from the different feature groups to create consistent snapshots of training data for clients. So if you want to look at the numbers for DuckDB, it's really well engineered. So the team who did this were the team that came from Monet. So in Amsterdam, they did the first columnar store. Monet was the first real columnar store. So they have a lot of history in the space. And if you look at the performance numbers in their latest benchmark here, that this is a DuckDB benchmark, but this is really for people who are looking at kind of data at reasonable scale. So you can see here Spark is down at, that we were looking at before, 129 seconds, and DuckDB is 8 seconds. In this particular case, it's a join benchmark with 100 million rows and 7 columns. So that's the kind of benchmark we're interested in because we know that that's one of the typical workloads we have in our feature store. And you can see that it's really promising. So that's great. If you want to use DuckDB in Python, this is all you need to do. You basically import DuckDB, obviously pip install it ahead of time, and then you can have query strings and execute them on the DuckDB instance. So it's pretty straightforward. And the interesting point is if you look at the last line here, you can see that we can actually get the data back in Arrow format. So DuckDB can actually process data that's in Arrow format. And we're going to exploit that later. We'll see that we can read the Parquet data up from our table formats, our Lakehouse formats, into Arrow, and DuckDB can process that data in Arrow format, and then we can return it to the clients, the Pandas clients, directly in Arrow format. So this is the service we built. We called it Flying Duck, which was really cool. We had a beard that had a flying duck in it, and we were really nice with the branding. And then DuckDB said, you're not allowed to use the term duck in any DuckDB products. And we're good actors, so we threw that in the bin. So we're just calling it like ArrowFlight DuckDB or something. ArrowFlight DuckDB, I don't remember what we're calling it. But it's a query service for querying feature data stored in the Lakehouse. And it's powered by DuckDB and ArrowFlight, all open source. So, excuse me. So this is kind of what we had before, just to put things in context. And this works, right? So you can use Hopsworks to kind of from a Python client, and it's great, but the performance, as I mentioned, is not great. So we have our Spark application here. It needs to read up the data from Parquet files, from the Lakehouse. It needs to deserialize it. We do a column row pivot. We do our join with this inefficient point in time join in Spark or Hive. Then we need to pivot our data back again, because we're going to send it as JDBC raw oriented data to the client, and we're going to serialize it. And in the client, we're going to deserialize it. And then Pandas wants it in column-oriented format, so we need to do a row column pivot again. We're using SQL Alchemy for this. There's a couple of libraries a little bit better, but it's still, you know, it's not high performance, let's just say. Now, there's another thing that this service does for us is it can also create training data. So sometimes when you're training models, your Pandas client isn't able to handle the data volume. Maybe you have, you know, billions of rows, and that's not feasible to return as a Pandas data frame. So you can materialize that training data as Parquet files or CSV or TF record. So that's another thing that we're doing in Spark, and we can also do now in DuckDB. So this is our new architecture. It is for reasonable scale data, as I mentioned. So whatever the memory capacity of the DuckDB server is, that's typically what we would recommend as the amount of data it can return. DuckDB does spill to disk in the latest version since I think 0.8, but that's not really super production ready. So we recommend keeping the amount of data returned to less than the amount of memory in that server. And if you want more, you can still use Spark. But you can see here is that when we read the data into our server, we're reading it directly from the Parquet files as Arrow data. And then we return, then we do the operations that we need to do. Maybe we can do push down filters as well to the Parquet files. Maybe we're going to do our join in here, point in time join, and then we return the Arrow data directly with the ArrowFlight protocol to the client. And the client, if it's a Pandas 2 client, can do a 0 copy of the Arrow data directly into the data frame, and you're good to go. This is pretty cool. So let's look at the challenges, and I'll show you some of the numbers at the end. Okay, so this is an enterprise service, so we're an enterprise company, so we have to kind of care about all the enterprise stuff. So I'll go a little bit through that. So firstly, we needed to do access control and authentication. You don't get that, of course, out of the box with the open source platforms. We're using mutual TLS for clients to authenticate themselves with the server. And we have access control lists inside in Hopsworks for the different projects that people are members of. That was all great. You know, at the back end, we do access control on we have a file system layer on top of the S3 where the table format is ultimately stored. So to do that access control within our file system, we needed to DuckDB to be able to read and write to our file system. Now, our file system is slightly different, right? So we are storing the data ultimately in a bucket in S3, but we write to that file system via HDFS API. We have our own file system called HopsFS, and it plugs into S3. And the benefit of HopsFS is that it's like you can think of it as being a globally consistent cache across all of the workers in your cluster. And you can read the data from there, from that cache, with NVMe speed. So instead of having to go to S3 and read it 150 megabytes per second, whatever, if you've got an NVMe disk there, you can read it potentially gigabytes per second. So we had to plug that into DuckDB. That was pretty straightforward because there was a connector for it. That's fine. What we also had to do was write a connector for Hudi. So one of the challenges with the Lakehouse file formats currently is Python compatibility. Delta Lake has a Python client called Delta RS, if I remember correctly. There's also one in the works for Iceberg called PyIceberg. They have read support now, but write support's not quite there yet. It's on the way. And Hudi is a little bit after, right? So there's neither any support for reading or writing with Python currently, so we had to implement reading. We're using Hudi copy on write tables, so it's a little bit easier than the merge on read tables in Hudi. But I'll show you a little bit of details how we did that. So Hudi tables consist of many different Parquet files, and there's a lot of metadata related to them. So every time you do an update to your Hudi table, you get a new commit and new metadata, potentially stored in different partitions. And when you want to read your data, in our case, we want to read the latest value of our features, so the latest commit. What we would do is we basically need to identify these Parquet files that make up that latest commit. So we did this efficiently ourselves, and this is not something we've released publicly because we're not super proud of it, but basically we're we're identifying the files with using our file system to do lists on the files. Now that's something that's very efficient in HopsFS. It's not something you would do on an object store because listing an object store is super slow and you only get back 1,000 files at a time. But in HopsWorks it scales order of magnitude faster. So that's how we get the current files that make up the commit, and then we need to basically serve multiple clients in parallel. So if we have a serverless platform with 4,500 users, what happens if many of them are reading data at the same time from the same ArrowFlight server? We need to somehow manage this. So one of the things we do is we set memory limits in DuckDB that if, for example, a user tries to read more data than is available on that machine, we'll throw an exception and tell them, hey, that was too much data, go and try and use Spark instead. That's pretty straightforward. The other thing we need to do is that we need to handle multiple concurrent clients reading. So what we do here is because each ArrowFlight server is independent, we can trivially load balance the requests across them. So just do a random load balancing pattern across those nodes. And we do that in the cloud. So that's pretty much it, and these are some of the numbers that we got out of it. Now, these are public benchmarks. They're for both the online feed. If you're interested in feature stores as a platform, a way of getting data for training and inference in your models, we have the feature store consists of 2 layers. You have this columnar store, the file format, or sorry, the Lakehouse format. That's what we call the offline store. But there's also an online store with low latency access. So you can get both of them at that GitHub URL, and you feel free to like it if you're there. But this is one of the benchmarks. This is the benchmark for the offline store. So it's a very well-known data set called the New York Taxi data set, which is about taxis picking up passengers and dropping them off. And you can see here we have 3 tables, and we can do a point-in-time join across those tables to create consistent training data. A point-in-time join is where you start with a prediction target or label, which we have in the raw data here. So we have a model we're training about estimating the fare amount, for example, and we'd like to include features from the pickup features and drop-off features in the training data set. So we're going to join them. But yeah, you can see here we have the observation of the fare amount, and we want to know those values for these particular features at that point in time. So what we do is we go back in time and we find the most recent value for that feature at that particular point in time, and we can see this for feature A and B here, and that's what the join is doing. So this is some of the numbers we have comparing HopsWorks with SageMaker, Vertex, and Databricks feature store, and it's pretty big, right? There's experiments in the GitHub repo for the different size of rows from 5 to 50 million. They're pretty consistent across all of them. As a Python developer, if you're using a feature store from one of these cloud vendors and you want 50 million rows, you can go for lunch and then come back and you get it as your Pandas data frame. It's not exactly super great user experience. But in HopsWorks now, you can get that back in 30 seconds or 20 seconds, which is it's a different experience. It changes how you can work with data, and particularly for data-centric AI, you want to iterate faster on changing different combinations of features and filtering out data and so on. This makes it very much a platform that you can work with interactively. The other thing you might want to do is your data might be bigger and you want to save your training data as files, Parquet files. This is an experiment. Again, we can still see a huge performance input, not quite as big in HopsWorks, but still much more significant. So here, for example, Databricks kind of works in this case, except for it didn't work at 50 million. So Spark works a bit better, so it's relatively okay at generating trained data as files compared to, in Spark, the problem they had, of course, with Databricks here is they're still doing this 2 pandas on the driver, which tends to blow up. So that's pretty much it. What I talked about here was how we want to improve feature store performance so we can get this Python-centric interactive development model working with feature stores. We want to basically help improve performance, so performance actually is important in changing how you work with a feature store platform. It should mimic your local workflow. And right now we're getting pretty much network line speed reading of data from the feature store, but our write path is still slow. So that's the next thing we're going to work on. The other point about this is that you still do need something that's really scalable for the really large workloads, and we still have Spark available for that. that's it. So if you're interested in find out more, you can go to visit Hopsworks. There's also featurestore.org that I organize, which is both a website and a conference. And you can find out more about them there. Thank you.
So, yeah, we have a couple of minutes for any questions you can ask here before going up to the island. Anyone? No?
There's one guy there.
So with the increases in speed and decreases in latency with this rewrite, do you still need a distinction between like an offline feature store and an online feature store, and why?
Yeah, we get this question a lot. So the basic idea of a feature store. So there was a feature store called Splice Machine, which is based on this hybrid OLTP OLAP. So it basically does both. So you have these hybrid columnar row-oriented stores. There's a single store is one of them, for example. The reason why they haven't been really successful is that there are a lot of use cases. I'll give an example, one, personalized recommendations, that are just really low latency. So if I'm doing personalized recommendations and I would go to, I would say, hey, I've just clicked on this link, or I've typed in some search query, what will happen in a kind of a state-of-the-art architecture is it'll go to a vector database, it'll get back a few hundred candidates, then it goes to the feature store with 300 or 200 rows, primary keys, and say, give me back 300 rows or 200 rows. And I need that in 30 milliseconds or 40 milliseconds. And the hybrid stores, columnar row-oriented stores, they're order of magnitude off there. So typically people, and this is a general trend we see this, that data volumes have been increasing for 30 years massively, and more specialized stores are just appearing all the time. And people said, graph database, I got Spark and GraphX, why do I need it? But, it's $1 billion market now. So I think just as data volumes increase, there's still always space for specialized databases that handle, popular workloads that there's demand for.